In this video, we are going over section 3.6, which is titled Getting Covalent Compounds into Shape. Now, in order for us to understand how covalent compounds get into shape, we need to remind ourselves of Lewis dot formulas, or in other words, Lewis dot structures for elements. Remember that these Lewis dot structures or Lewis dot formulas illustrate the valence electrons in an atom. Remember that for representative elements, those are going to be the digit before the letter A, specifically for groups 1A all the way through 8A. The only element that their group number does not correspond to their valence electrons is going to be helium because it only has 2. So that's the only exception. But for the rest of the elements, they are following those rules. Now, first, we can observe that we can actually have electron dot formulas for ionic compounds. Even though in the slides, I actually have some examples on how to do them, understand that we are mainly going to focus on the covalent compounds. But still, let's illustrate how we actually show that an ionic compound is formed. So let's say that, for example, we are talking about the ionic compound calcium chloride. Calcium chloride has the chemical formula CaCl2. So what this means is that we are going to have a calcium atom actually giving electrons away to chlorine atoms in order to produce a cation, which is going to be the calcium, because since it's lost 2 electrons and each chlorine got 1, we form 2 anions of chlorine, and this is how we illustrate how calcium transfers its electrons to chlorine. Please remember to review how we form ionic compounds from part 1 of this video series in order for review how this illustration for ionic compound actually comes to life. Now, when it comes in the case of molecular or covalent compounds, let's understand that remember that they are going to share electrons. Here we have the electron dot formula for the diatomic molecule fluorine. So fluorine is a gas, and as you can see, this is a fluorine molecule. I mentioned previously how there is a series of elements that are going to be found in diatomic form, and here you see them illustrated again. Hydrogen, which is mostly formed as a gas, that's why you see the symbol G in parentheses, is a diatomic molecule. Nitrogen, which is also a gas. Oxygen, which is a gas. Fluorine, which is a gas. Chlorine, which is also a gas. Bromine, remember that is mostly found in liquid form, and iodine is also found as a solid. So that's why you see it below bromine and L, that's cursive L, and then below iodine you see an S. That's just representing the state of matter for these diatomic elements. So let's get back to the fluorine example. So when it comes to fluorine, let's understand that each fluorine atom is going to have 7 dots. And that's because fluorine is in group 7A of the periodic table, and those are its valence electrons. Now, When these two fluorine atoms come together to make a fluorine molecule, those electrons that you see are pointing, the different arrows, so this one and this one, are the electrons that are shared between the two fluorines in a fluorine molecule. So we can see, I'm going to use my highlighter, that here we have what is called a bonding pair of electrons. And a bonding pair of electrons is another word that we can utilize in order to mention a covalent bond. So that bonding pair of electrons is what it can also be represented by a line. So any pair of electrons that are shared between two elements, we can illustrate them using a line, and that's going to be the conformation that we mostly utilize. Now, each fluorine atom is going to have, as you can observe, different dots around them. So those dots that you are observing, and you can see here, this fluorine has 3 pairs of dots. This fluorine has 3 pairs of dots. Those are called lone pairs. And the lone pairs are specifically unshared pairs of electrons. So those electrons pertain to each fluorine molecule. So overall, we can see that at the end, you see the chemical formula for the fluorine molecule, and this is just a representation utilizing a molecular model that those yellow spheres are going to represent the fluorine atom. So when we have this information, we can actually predict what's going to be the shape of different chemical formulas for covalent compounds. And this is the process to which we have to take into consideration when we're building such structures. Understand that these rules for drawing Lewis dot diagrams or Lewis dot structures are going to be specifically a reference list. This is the way that I teach it. So make sure that you review these rules. So number 1, we're going to add up the total number of valence electrons for each atom in the molecule. At times, we will be dealing with molecules that have signs, and these signs represent the overall charge for that molecule. Remember that we are dealing in essence with polyatomic ions, and because they are formed by nonmetal elements, they are covalent compounds, even though when you mix them with a metal, overall, the compound is ionic. But a polyatomic atom by itself is a covalent compound. So if they have a negative sign, that corresponds to 1 electron. So if you have a covalent or a polyatomic ion, I should say, that has a charge of -2, that means that you're going to then add 2 electrons to the total number of valence electrons. We will see an example in a moment. Now, if your polyatomic ion has a positive charge, remember that we have ammonium as our positively charged polyatomic ion, then you're going to subtract 1 electron for it. You're going to write the symbol for the central atom, and then you're going to use 1 pair of electrons to form bonds between the central atom and the remaining atoms. One of the ways that we can detect what is going to be the central atom is by a trend that we are going to learn in a few moments, which is called electronegativity. So that central atom usually is identified by the least electronegative atom or the least frequent atom in a chemical formula. So the central atom, let me just make a note here. Least electronegative atom or least frequent. The least frequent refers to, it has the lowest subscript within the chemical formula. Now we have built that skeletal formula. That's what step 2 is. We're going to count the number of electrons remaining, and we're going to distribute them according to the octet rule. Understand that the majority of the elements want to have an octet. In a moment, we're going to talk about the ones that do not. If there are not enough pairs of electrons, make sure that most electronegative elements are satisfied, and then we're going to start shifting pairs into double bonds and triple bond to satisfy the octet. And this is especially if the central atom does not have an octet. And then in the case that all the other atoms, once you have satisfied their octet, if there's extra atoms, you just place them in the central atom. As I mentioned, there are a few elements in the periodic table that actually don't need 8 electrons in order for them to achieve noble gas arrangement. Let's talk about those exceptions. The 3 that you guys must remember are hydrogen. Hydrogen actually only wants 2 electrons. And hydrogen is never a central atom with other nonmetals. The only time that, quote unquote, we see hydrogen as a central atom is if you're looking at the Lewis structure of H2, and the Lewis structure of H2 is hydrogen sharing 2 electrons with another hydrogen molecule. Beryllium, even though it lives in 2A, it actually forms covalent compounds. Moreover, it actually requires only 4 electrons to form a noble gas arrangement. Lastly, boron. This is a metalloid from group 3A. It actually requires 6 electrons to form a noble gas arrangement. Beryllium and boron, we typically see them as central atoms, specifically in covalent compounds. Let's do examples of how to write the Lewis structure for different compounds that are covalent so we can apply the rules that we learned. For this, I'm going to specifically do examples B and E in the slide. Let's get started. If you have a chemical formula, the first thing that you have to find is what are going to be the valence electrons available for bonding based on that chemical formula. So as we observed here, in the case of beryllium bromide, we're going to write how many electrons are provided by beryllium, how many electrons are provided by bromine. Beryllium lives in group 2A, and as I mentioned, that's an exception to all the elements in 2A. Remember that for the most part, most elements in 2A form ionic compounds. Beryllium is the only exception that it forms a covalent compound. So beryllium we only have one beryllium, because you can see that there's no subscript next to beryllium, so that means it has a value of 1. And because it lives in group 2A, there's 2 valence electrons provided by the beryllium. Bromine, on the other hand, has a subscript of 2. And because there are 2 bromines and it lives in 7A, 7 electrons are provided by each bromine. So when we do this, we are going to multiply 1 times 2 electrons. So beryllium contributes 2 electrons. Bromine specifically is going to contribute 14 electrons. When we add these 2 values, that means that in this molecule, there's 16 electrons available for bonding. Electronegativity will be specifically in the next video, but for now, understand that the least frequent atom, in this case, beryllium, because we only have one of them, that's going to be our central atom. Later, when you see electronegativity, you will see that beryllium is going to be less electronegative compared to bromine. But for now, beryllium is our central atom. Now that we have beryllium as our central atom, according to the rules, we're going to create the skeletal structure, meaning that we're going to attach bromines to our central atom. These lines that I have are representing 2 electrons. So I already attached 4 electrons total, because 2 from the left, 2 from the right. So overall, I already attach 4 electrons in my skeletal structure. So I have 12 electrons available for bonding, for building this Lewis structure. I have to complete the octets of the most electronegative elements. Understand that that's another word to say complete the octets to the outside elements first. So taking that into consideration, if I complete the octets of the bromine on the left, then I'm going to specifically say, well, it needs 2, 4, 6, and then these 2 that is sharing, it has 8 electrons. So that bromine on the left already has its octet. Since I added 6 dots, that means that I already used 6 electrons out of my count for bonding. So there's 6 electrons left. Let me highlight them. So people can keep track of the electrons and where they're going. So there's 2, 4, 6. These are these 6 electrons. The bromine on the other side also requires 6 electrons. So we're going to place 2, 4, 6 electrons, because overall it has 2, 4, 6, and then the 2 that is sharing with the beryllium, those are the 8 electrons in that bromine. So since I place 6 dots, I'm going to subtract the 6 electrons that I placed on the bromine on the right. So I used all my electrons available for bonding. As I just mentioned, since beryllium only requires 4 electrons in order to obtain its octet, then that means that we are done with the molecule. That you see here is the Lewis structure for beryllium bromide. Let's do one more example. Here we have carbonate. Let's first find the valence electrons available for bonding for carbonate. In the chemical formula of carbonate, I have carbon and I have oxygen. Carbon lives in group 4A, and there's only one carbon in this chemical formula. So there's 4 electrons that carbon is contributing. Oxygen, there's 3 of them because oxygen lives in 6A. Then 6 electrons are going to be contributed by the oxygen. So at first, when I multiply by the subscript, I see that there's 4 electrons from the carbon, 18 electrons provided by the oxygen. So when I add these two values, I observe that there's 22 electrons available for bonding. Now, since this is a polyatomic ion, and I see that overall, there is a charge of -2, that means that to my count of valence electrons, I'm going to add 2 electrons. So in this chemical formula, there's a total of 24 electrons available for bonding. So that was just the little bullet point on rule number 1, and this is how you apply it. When it comes to finding the central atom, as you can see, right now, carbon is the least frequent atom, so that's going to be our central atom. And then we're going to attach the 3 oxygens around it. I'm doing this type of arrangement just because of space. Now, if you decide to just put 2 oxygens, one in the left and one in the right and one on top, that's correct. If you decide to put one on the left, one on the right, and one pointing down, that is also correct. So when it comes to Lewis structure, I chose to draw this because of space. So this is my skeletal structure. So take a moment and find out how many electrons are already attached to this skeletal structure in the molecule and the skeletal structure for carbonate. So if you predicted that there are 2, 4, 6 electrons that were already utilized in the skeletal structure, you are correct. So if we subtract that from the total count of electrons, then we have 18 electrons left. So when we do this, we have specifically 18 electrons left for bonding in this molecule. When this happens, let's understand that now we have to complete the octets of the outside atoms first. So each oxygen atom, because they're already sharing 2 electrons with carbon, they will receive 6 electrons in order to complete their octets. So when this happens, we have 2, 4, 6 electrons added to the first oxygen, 2, 4, 6 added to the next oxygen, 2, 4, 6 electrons added to the third oxygen. Now all the oxygen had 8 electrons, and we utilize the 18 electrons that we have available for bonding in this molecule. So we don't have any more dots that we can add, in other words, lone pairs. So let me just use my highlighter tool. To show the 18 electrons in the system. Now, there's one more step missing here, and that is that specifically, out of all the atoms here, each of them are not meeting the exceptions that I mentioned in a moment. Each atom here, carbon and oxygen, must have an octet. Right now, we can observe that the oxygens have 8 electrons. The only atom that is missing an octet is carbon. Carbon only has 2, 4, 6 electrons around itself. So In order to complete the octet of carbon, one of the oxygen atoms has to bring in a pair of electrons and share with the carbon atom. So when that happens, this leads to the creation of a double bond. And overall, this double bond now means that that oxygen in the top is having 2, 4, 6, 8 electrons, and it has a full octet. And now the carbon atom has 2, 4, 6, 8 electrons around its shell. Now, every atom in this compound is happy with the correct number of electrons filling their octet. Understand that the oxygen on the top was the one that I selected, but the oxygen on the right, the oxygen on the bottom could have also shared in its electrons. I just selected the one on the top just to illustrate this example. Make sure that you practice how to draw the Lewis structures of the other examples that we have on the slide.